So that's kind of the game plan. So one of the things I want to finish up in this part 8, is this idea of what seems to be equal is not necessarily equal. So up here we have methane, ammonia, and water. And these are actually the Lewis structures of those compounds. And if you were to look at the central atom, the carbon, the nitrogen, and the oxygen, you could see that we're looking at sp3 orbital hybridization, because they have 4 things, whether they're sigma bonds or lone pair electrons in each case. Okay, and so you're going for that 3rd row, okay, sp3 orbital hybridization, so you're going for tetrahedral shape, okay, at least the structural geometry, what we call electron pair geometry around those atoms, and you're going for a bond angle of 109.5. So the thing is, though, is they are not, like I said, all necessarily equal. When it comes to electrons, and this is what you're going to see, electrons, lone pair electrons, okay, they actually take up, I'm going to just say, more space. Quite simply, I never thought of it like that. They take up more space. And so actually you're going to see that consequence when it comes to looking at kind of the real bond angle, okay? So, for instance, methane, that has the central carbon atom with 4 hydrogens, okay? So those are all equal, and that actually is the that's tetrahedral, 109.5, okay? But when you get to ammonia with 1 pair of lone pair electrons, that pair of electrons kind of make those legs of those hydrogens kind of scoot together. So instead of 109.5, you got 107. Okay? On a test, if you put 109.5, that's what I'm looking for. But in reality, it's a little bit less. And then, of course, for the water molecule, which I always call the Mickey Mouse molecule, okay, so because the hydrogens are like the ears of Mickey Mouse, and the oxygen is like the face of Mickey Mouse. But anyway, they take up even more space. So actually, you can see instead of 107, the bond angle between, those, putting the oxygen at the vertice and the 2 hydrogen, that's actually 105. Okay, but if you tell me on a test that you know that the hybridization of that oxygen atom is sp3, and if you put 109.5, that's what I'm looking for. But really, it's less than that. Okay. So these kind of. So we skip a few slides, I think. I'm not sure. Kind of lost track. But just to kind of finish out your notes, one of the things that you guys did yesterday, okay, is this sort of thing. We're actually, if we're looking at what each one of those carbon atoms are doing, it's symmetrical. They're both doing the same thing. Of course, you would, if I asked for hybridization around a carbon atom, you'd say one of those covalent bonds with a double bond is sigma. Oops, one of them is sigma, and the other is pi, so it doesn't count. We have sigma bond, sigma bond, sigma bond. So actually, we must have sp2 orbital hybridization. Okay, and then everything else kind of falls into place for either carbon that you pick. In this case, anytime you see a triple bond, only one of those bonds is sigma bond, and it participates in hybridized orbitals. Okay, so actually we must have sp orbital hybridization here. Okay, and that means that it's linear and the bond angle is 180. So hopefully you're kind of, and actually you're getting a sense for, you can look at the Lewis structure and go atom by atom and get a sense for what the shape is around the atom based upon the Lewis structure, the orbital hybridization, okay, and then actually you can assemble the shape of a molecule. So you're going to get some work at that for your homework at the end of this part. Okay, so this is ethylene, and actually, while I'm mentioning it, and I just want you to do your best, but at your homework, for instance, you're going to be drawing Lewis structures like this, and maybe it's not so obvious, but this is an example of a molecule that actually would fit in a plane. Okay, we have trigonal planar. Anytime you see bond order 2 or 3 like this, there's no rotation. Okay, Okay, I haven't said that before, but there's no rotation. There generally is rotation around a single bond. Okay? And so actually that thing lies in a plane. Ethylene again. Those pictures of ethylene reminded me that, C, double bond C with four hydrogens, two on each side, reminded me of like a parent who took too many pictures of their child. Okay, so let's take a look at these that are going to be due then on Monday. We're going to get to this problem set, the next problem set, and of course your Lewis structure for lab credit is also due Monday. So this looks like this. Okay, so I have some hints, and I'll push these hints out there. That's easy. By the way, I need to apologize. I don't have the book in the library up to date, but I figure as long as I update it Monday, no one between now and Monday is going to go look at the book in the library. But from my home, I will try to go ahead and release the homework solutions. So if you're at home wanting to get to those, you can. Okay, so 7 and 8, I kind of grouped together. Now, my hint for number 7 is just to draw the preliminary, I said I'm giving you for B, that is the preliminary structure of HONO2. That you might find helpful. This is my first semester say, oh, I bet they would like to have that. Maybe I did that last semester, I don't know. But for the exam, when I have you draw a Lewis structure, it'll be just like it was for lab. There'll be a middle atom, okay, and then you'll draw atoms off of that. That one, B, you needed some help, okay? So I've drawn in kind of the arrangement basically for you. It's not the final Lewis structure, okay? So in blue, I say all other structures have a central atom. So 7, basically, they want to, and this is kind of the theme for throughout this homework, they want you to go ahead and propose, well, I guess I should put it this way. Whenever it says propose a hybridization scheme, I want you to focus on the central atom and explain its hybridization. Okay? Hybridization scheme, central atom. You guys will be dreaming Lewis structures. Okay, so there's A, B, C, and D. The next one, it's really similar. Oops, sorry, go back. The next one, the NSF, very similar. Come back here. Okay. So I say draw the Lewis structure and describe the hybridization of the atom that's in the middle. By the way, I double-checked my notes. Yes, sulfur is actually between nitrogen and phosphorus and fluorine. Nitrogen and fluorine for that. All right. The next pair look like this, where describe the hybridization scheme. I love that word, scheme, for the chlorine atom when it bonds to 3 fluorine. Okay. Now, here's the deal. When you come up with a pot of valence electrons for that chlorine surrounded by 3 fluorines, you are going to have a boatload of electrons. And you're going to see that you are actually going to give the central atom, which is the chlorine atom, an expanded valence. I don't have it written down here, but instead of a complete octet, we'll look for whatever you put for the word 10. Look for 10 electrons around the central atom, sp3d. Okay? So number 10 is kind of similar, where you'll have the sulfur in the middle, the 4 fluorines, and you're going to have, sulfur is going to have 10 electrons around it. Okay? So my hint in blue over there is go ahead and, especially the first step we did in yesterday's lab, come up with a pot of valence electrons. If you don't do any of the other kind of like steps 2, 3, 4, or whatever, I would do that first step. Sometimes you can almost eyeball a structure and I know what that looks like. And maybe you do, but see how many valence electrons needs to be distributed around the Lewis structure. I did it again. Okay, so the last page looks like this. If it would just read my mind. Okay. No, I guess I broke it up into 2. So you can see like in the green and the purple there, I went ahead and tried to expand that kind of shortened structure so you would know. And maybe you already knew, but like for instance, you're going to need to draw the Lewis structure of methanol or methyl alcohol, the same thing, B. And whenever it's a way to kind of show functional groups when they write the CH3, basically they're saying carbon with 3 hydrogens around it, like you see up there. The OH is a hydroxyl group, and it kind of kicks off the carbon. So I went ahead and drew in the sigma bonds. Okay, so I'm hoping that's helpful. Again, these are not the final Lewis structures. All right. So just go ahead and write the Lewis structures. And then the last one, I bet you would have gotten A. Again, I showed that that these 2 chlorines actually are kicking off the carbon. Those 2 chlorines are kicking off the carbon. Again, these are not necessarily the final Lewis structures. Okay? So, LOL. Now we can go ahead and break out and go to the lecture slides. Nope, wrong one. Okay. Part 9. Okay, the Bragg list again. Well, I guess this isn't the Bragg list of how you can use Lewis, what you can use Lewis structures for. This actually, I'm going to hurry through these next few slides because you're like, oh, okay, I know the steps in making a Lewis structure. Okay, but actually, I mentioned the Bragg list because I think a few parts ago there was a Bragg list of once you draw the Lewis structure, you can blah, 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 blah. One of those things that you can do from a Lewis structure is to come up with the formal charge of each atom, and that's what this part's talking about. So we said, for instance, we did this example, the formate ion, we said you have to have the positive valence electrons. Again, I guess I haven't thought about it too much, but even if you don't do all the steps we did in lab, do this step on whenever you're faced with drawing a Lewis structure. Okay, so these are the initial sigma bonds, so this is the preliminary structure. There's only 6 electrons represented there. Okay, so we have actually 12 remaining, and we did this before. Now this is where I'm breaking off to do something a little bit new. When we did this before and you did this in lab, you knew to go ahead and give the carbon a complete octet, you needed to swing lone pair electrons. And actually one of the ones with the neutral molecule you did in lab, you knew to swing from the oxygen instead of a chlorine because oxygen wants to reach out twice. Its expected valence is 2, expected valence of a chlorine atom is 1. But this, it's like, dude, I don't know, which oxygen, right? Well, actually, this is charged. This is a -1, the formate ion. So the expected valence of oxygen goes out the window anyway. So my point is going to be you can choose from either. Okay, we just chose from the north one. But in reality, what I've done kind of side by side is those 2 scenarios. If you look at them closely, what's different about these 2 is where I swung the lone pair electrons from. In this case, I swung them from there, and in this case, I swung them from there. In both cases, the carbon atom gets complete octet. In both cases, you kind of have the, the 1 oxygen reaching out twice, 1 oxygen reaching out once, which is fine because we don't follow the expected rules of valence for an ion like this. These actually are resonance structures. Sounds like a good thing to put on a test, huh? All resonance structures is they differ from where you convert a pair of lone pair electrons to form a pi bond. So they're Lewis structures that differ only by where the conversion occurs. Okay? So these are resonance structures. Aren't they wonderful? So, actually then, we can, probably as you might imagine, if anybody puts a 2-way arrow up there like that, you're like, oh, I guess it goes back and forth, and it does. There actually are these things we've talked about chemical equilibria before, because we said sometimes it's hard to get 100% yield because basically the products go back to form reactants, reactants go to form products. That's kind of what we have going back here. So honestly, in reality, I'm going to use the word electrons become delocalized as to kind of describe that the situation with formate is probably something in between. It's not absolutely structure A, and it's not absolutely structure B. If on the previous slide you kind of show where you swing your electrons from, where it is somewhere in between, okay? I don't know if this is a good analogy or not. The electrons become what we say delocalized. If we have two very valid Lewis structures like that, because what was the difference between A and B? Nothing. What is so cool though is actually you can make those two oxygens where you swing it from, you can make them different isotopes, isotopically unique, so you can tag them and know where the electrons come from. I think that's exciting. My favorite molecule that does this delocalization of electrons is the benzene. Benzene ring. Seems like you can't say the word benzene without saying benzene ring. Okay, so what you're looking at here is C6H6. We have a, really? Oops, dang it. Benzene. There, that's better. Okay, so it has 6 carbons in a ring. 1, 2, 3, 4, 5, 6. 6 carbons in a ring, and they alternate single, double, single, double, single, double. That's one of the ugliest benzene rings I've seen. Okay, but that's my benzene ring. It's cyclic and it alternates single, double, single, double, single, double. And then the hydrogens are adorable. They kick off of each one of the carbons. So this actually is using correctly the pot of valence electrons that molecule has, okay? And if you kind of isolate any carbon atom, it has a complete octet. Octet, octet, so that's it. It's kind of ugly, but that's my benzene ring. But here's the deal. Oh, by the way, then the other thing that we do with benzene, or with drawing structures in general, and if you take general chemistry too, or organic chemistry somewhere down the road, they'll probably say there's so much chemistry with carbon that instead of drawing those little carbons, we basically can just kind of, anytime you see a kink in a lines, okay, each one of those kinks is a carbon. I don't know if you can see the kinks. Each one of those little bends is a carbon. Okay, so they do that a lot. So for instance, like if you had, let's see, if you had C2H6, now let's go ahead and put C3H8, C3H8. It would look like this, kink, kink. Carbon, carbon, carbon. Okay, and we'll probably put hydrogens there. But that's why this is drawn over here, just to explain, that's a benzene ring. So they're trying to show the single bond between carbons, double bond, single bond, double bond, single bond, etc. But like we said before, you know, which one is right? They look the same, but if you look, basically the double bond has shifted one over. It's still alternating single, double, single, double. So this is a good example. If you've ever taken a, I don't know if this will work for you, but like a bottle, like a glass bottle, and you wet your finger, and you go like, I guess you can do this with martini glass too, and go like this, and you kind of get the, okay. You are actually, I don't know, it's a physics thing, but you are actually creating a resonance, so it makes that sound, okay. And that's what I think of basically electrons, those pi electrons that are delocalizing, kind of like you dislocate your shoulder, delocalizing, dislocate, and basically they are kind of buzzing around. The benzene or the benzene ring is very reactive. It's like it's involved in a lot of chemistry. A lot of bad chemistry, good chemistry. So anyway, that's my favorite stuff that has, that definitely has resonance going on. Okay, so it's possible though that you can draw a structure A and a structure B from the pot of valence electrons. You can draw a pair of resonance structures, and one of those makes a lot more sense than the other one. An example would have been in your lab if you had swung a pair of electrons from the chlorine atom to satisfy the central atom, okay, instead of from the oxygen. That didn't make as much sense because of what we expect oxygen to reach out twice and chlorine to reach out once. But Those would be resonance structures using the available valence electrons, spreading around your atom, around your molecule. So when we're looking for the correct Lewis structure, okay, this is kind of a checklist. You want atoms to have a complete octet. Okay, you want things like nonmetals to be partially negative. If I use partially in here, I think I have. Okay, since metals tend to be higher electronegativity, they like to tend to have custody of electrons. You would expect metals to be what we say partially, this is the term for partially negative, and nonmetals to, oh darn it, I said that wrong. We expect nonmetals to be partially negative. Final answer. And metals to be partially positive. And actually, with this part that we're going to talk about, this idea of formal charge, that's kind of what we're looking at. Okay, and when we go ahead and come up with formal charges, it's okay to have electrons kind of being over here a little more than electrons over here, partial negative, partial positive. But you don't want to have a drastic change within the same molecule. Okay. So this again goes back to what you guys did in lab. You drew electrons from the oxygen atom. You converted lone pair electrons from the oxygen atom because you knew its expected valence was 2. Chlorine was expected valence was 1. So if I were to, most classes, if I were to say structure A or structure B, you probably pick structure A, seems better. And it does seem better. Actually, again, back to the expected valence of an oxygen atom, B does not seem right. A lot of times we tend to gravitate towards symmetry too, so that's also structure A. But I will tell you, these are resonance structures. It's just that one is basically not so much an ingredient in the reality of CO2. All right. So once you draw your Lewis structure, one of the things on the checklist of things you can do with a good solid Lewis structure is you can go atom by atom and assign a formal charge to the atoms in your Lewis structure. And I'm going to show you just kind of an easy sort of, it's a little subtraction problem. It kind of reminds me of effective nuclear charge, though I guess it's a little different. Okay, it's way different. But it's a little subtraction problem, and you do it for each atom in your molecule or polyatomic ion. And the number you come up with will have a plus or negative, and it will have a magnitude, and actually that's kind of in general the charge that's on that atom in that molecule. So here's the deal. It's the charge on that atom in the molecule or the polyatomic ion. If we assume all covalent bonds are non-polar. Polar covalent bonds, by the way, are where basically electrons spend more of their time on the atom with the greater electronegativity. So a non-polar covalent bond is basically going to have total half custody of the pair of electrons that's connecting those two atoms. Okay? And that's what you're going to see here. So I mentioned this little subtraction problem. So in your homework or whatever, if you're asked to calculate the formal charge, what you do is you go to the periodic table. That's supposed to be a periodic table. You look at what group it's in, and you pick up the valence electrons. That's for that atom. Okay? I still didn't go there. And then you look at the Lewis structure, and I'll show you how this goes. but this is from the Lewis structure. Then you go ahead and do a bit of divvying up of electrons as they're distributed on your final Lewis structure. And wherever there's a covalent bond, whether that's a sigma or pi bond, you go ahead and you split those electrons equally. One electron goes to atom A, one electron goes to atom B. If it's a double bond, you go 2 and 2, okay? So they all share it. And like this says down here, if in your Lewis structure you have an atom that has a dot, a pair of lone pair electrons with that atom, it gets full custody of those electrons. No need to split it, okay? So this comes from your Lewis structure. This comes from the periodic table, whatever the subtraction is, and positive and negative does make a difference. Okay, so we're going to do an example coming up. So formal charges. Formal charges are a way to look at Lewis structures and to see if they make sense. Okay, so you're really kind of after the most calmest formal charges possible. Zeros are great. Zeros across the board are great. And I kind of mentioned this before, that you should have negatives on your nonmetals, if there are any negatives, if they aren't zero, and you should have positives on atoms that tend to have low electronegativities. Those would be your metals. If you don't, something's probably wrong. When you're done finding the formal charge for all of the atoms in your structure, and if your structure is a neutral molecule, okay, you add up all the formal charges and they should add up to 0. If you are finding the formal charges for atoms in a polyatomic ion, you should add them up and they will be the charge of the ion. Those are kind of the rules. That makes sense. It's easier to show you, I think, and I'm only going to do one example. So this seems a little hokey because we know that life isn't all about non-polarity. We live in a very polar world, okay? But it's helpful. And it can definitely tell you what's going on with regard to the electrons in a molecule. So let's just pick on this structure. So this is the pot of valence electrons, where those valence electrons are supposed to go in this structure. So for each one of these atoms, we are going to go ahead and calculate the formal charge. Okay. So first, let's go ahead and come up with the second number. That second number, we're going to use the Lewis structure to come up with, for each atom, what electrons it has. Okay, starting with this oxygen up here at the top. So in this kind of blue circle, actually, you see 2, 4, 6, 7 dots. Okay, that is actually the 7 electrons at the nonpolar limit. Okay, and here in a minute we're going to, of course, you find oxygen in 6A, so we're going to take 6, its valence electrons, minus 7. So actually it's going to have a formal charge of -1 here in a minute. That's how that's going to go. But do you see how it actually has joint custody with with a pair of electrons, okay, with the nitrogen atom, and they split them up? That's how that goes. So let's pick on, I think the next one's hydrogen. Okay, so around hydrogen, it's only got a pair of bonding electrons to the oxygen. So of the 2 electrons, it gets 1. By the way, valence electrons around a hydrogen atom is 1, so 1 minus 1, hey, that's going to be 0. And then I think I skip over to this oxygen. Okay, so this oxygen, of course, it keeps the 2 pairs of lone pair electrons because it had it on a Lewis structure. And here we have actually a sigma and a pi bond to the nitrogen atom. So we have 4 electrons, right? And it's got to split them down the middle. So it gets 2, And in a minute, we're going to see nitrogen gets 2. So let's see, if this is we subtract from 6, we subtract 6, so hey, it's actually going to have a value of 0. So then on to this oxygen here, you see it's 2 pairs of lone pair electrons, it's north and south. And over here you see this is 1 electron from the pair of electrons it shares with the hydrogen atom. And this is 1 electron from the pair of electrons it shares with the nitrogen atom. And last but not least, nitrogen has no lone pair electrons. Okay, so it has 1 electron from this sigma bond, 1 electron from the sigma bond from the north oxygen, actually a pair of electrons from this double bond with this oxygen. Okay, so those are electrons at the nonpolar limit. All right, ready to go ahead and knock out what their formal charge. I can never remember what formal charge is. So on this Lewis structure, that north oxygen, of course, oxygens have 6 valence electrons, group 6A. And in this particular structure, it has 7 electrons at the nonpolar limit. 6 minus 7 is -1. Okay, hydrogen, 1 valence electron. In this structure, it has 1 electron at the nonpolar limit. It has a formal charge of 0, which is wonderful. Over here, we said this oxygen over here also has a formal charge of 0. 6 valence electrons, 6 in the structure. Okay. Then we pick on, I think, that oxygen over here. Okay, it ends up with 6 electrons at the nonpolar limit. We subtract that from the valence electrons. And then here, one last guy. Okay, nitrogen is a 5A element, so it has 5 valence electrons. In this particular structure, it has 4 electrons at the nonpolar limit. So it has a formal charge of +1. So do you see one of the rules we said for a neutral molecule like this, when we add up all the formal charges of all of our atoms, it better be equal to 0 since it's neutral. And it is 0. And it's not too crazy out of proportion. Okay, if you had a formal charge of like -5 over here and positive 5 over here, it's probably not the correct Lewis structure. But one of the things that we can say, even with that the formal charge of -1 and the formal charge of +1, is there is a degree of disproportionately electrons are going to be hanging out here more than they are here. And in general chemistry, too, we talk a lot about how molecules stick together, and the polarity is important. So this would be partially negative, and this would be partially positive down there. All right. So let's look again at those 2 Lewis structures, A and B, for carbon dioxide. And we can come up with the formal charges of the 3 atoms in both cases. Whoops. Okay, so in this case where it was symmetrical, and we would all kind of tend to think that actually the carbon is doubly bonded to 2 oxygens, both oxygens, and then both oxygens have 2 pairs of lone pair electrons. And if you do the exercise we just did, okay, since the number of valence electrons around an oxygen atom is 6, so 6 minus 6 is 0. You know, carbon's a 4A element, 4 valence electrons, 4 minus 4 is 0. So hey, if we compare that to this sort of deal, where you have carbon, single bond oxygen, and triple bond oxygen, we have something a little bit different. So over here, we have at the nonpolar limit 7 electrons. So 6 minus 7 is -1. Okay, for the carbon, the formal charge is still 0, but for this oxygen over here, it is 6 minus 5 or +1. Okay, so this doesn't make as much sense. It's not as good. Okay, so let's take a look at these. They're not bad. I sure, you said that, right? Okay. Part 9. All right. So this is 17 and 18. And I really think you should just, find your happy spot, and I would go ahead and redraw these, okay? I just think it's hard to say, well, the middle carbon, blah, 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 and the end carbon, But do exactly what we did in lecture for each of these atoms in these molecules. And I went ahead and gave you a couple of hints for C. For C, notice we kind of pack it up. That C, anytime you see CH3, that's called a methyl group, THYL. And so actually what it really means is carbon is singly bonded to 3 hydrogens. We kind of call this the carbon chain, carbon bonded to carbon, bonded to carbon. Notice that it's all running around with a +1 charge. Anytime you're dealing with assigning formal charges to atoms, and it's a polyatomic ion like this, they should add up to be equal to the charge there. Okay? And then C above. Let's see. 47 and 48. 47 says draw the, I would suggest you go ahead and draw the Lewis structure for NO2 negative, the nitrite. And then, and what you're going to do, yeah.
On the previous question, the middle carbon should only be bonded to 1 hydrogen.
Thank you. I was like, thanks. I was like, that doesn't make sense. Good call. Because otherwise, that's not going to work. Okay. Any questions? That's the one that will be posted. Okay, so for 47, you're going to see that of those 2 oxygens, you can swing from either oxygen. So for 47, I would just write the Lewis structure A and the Lewis structure B, and they are going to be kind of similar to that formate ion. And for 48, I said to answer this, I really think you will need to draw the Lewis structures, because basically they're looking at which of these would have possible different resonance structures. And is that it? I guess so. Seems like there was another page. Oh yeah, there is one more page. But I didn't say. What's the last number on your thing?
48.
What, 48? Oh, all right. Okay, good. Have a good weekend, everybody. There's some sort of grand something going on at 4, so.
So we have, do I have the